Hi, good evening. I'm back again with you. We're a sequel to yesterday's glycolytic cycles. We're over to the citric acid cycle, right? And the citric acid cycle, as you can see, we know by now that glycolysis takes place in the cytoplasm and leads to the formation of two molecules of pyruvate per molecule of glucose. These pyruvate molecules are converted to acetyl coenzyme A, also known as acetyl-CoA, and this happens inside the mitochondrial matrix. Therefore, acetyl-CoA is the key metabolic intermediate that links glycolysis and the citric acid cycle. For clarity, we will not show the coenzyme portion of acetyl-CoA this time. Instead of simply representing it as a two-carbon molecule acetate. So how does the pyruvate get into the mitochondrial matrix? This depends on a carrier protein that transports pyruvate into the mitochondrial matrix, where there it is oxidized to form acetyl-CoA by the enzyme pyruvate dehydrogenase. In this reaction, a molecule of carbon dioxide is generated as pyruvate, is oxidized to acetyl-CoA, and a molecule of NAD+ is reduced to NADH. That last reaction is not shown for clarity. The citric acid cycle consists of the following 8 steps and also harvests chemical energy producing a total of 3 NADH molecules. In the first step of the citric acid cycle, the enzyme citrate synthetase combines the 2-carbon acetyl group to form acetyl-CoA with 4-carbon molecule oxaloacetate. This generates the 6-carbon molecule citrate. In the second step, citrate is isomerized into isocitrate by aconitase. In the third step, isocitrate is oxidized by isocitrate dehydrogenase, generating the 5-carbon molecule alpha-ketoglutarate, generating in the process 1 carbon dioxide molecule, which is released, and 1 NAD+ molecule is reduced to NADH. In the fourth step, alpha-ketoglutarate is decarboxylated and oxidized to produce another molecule of carbon dioxide by alpha-ketoglutarate dehydrogenase. The resultant molecule is combined with the coenzyme A, forming succinyl-CoA. In addition, another molecule of NAD+ is reduced to form NADH. Note that in this diagram we are showing the product of this reaction is as succinate and are omitting the coenzyme A for clarity. In the fifth step, succinyl coenzyme A is converted into succinate by succinyl-CoA synthetase releasing coenzyme A. This reaction is also producing 1 molecule of GTP, another high-energy molecule, which is omitted from this diagram for clarity. In the sixth step, succinate is oxidized to fumarate by succinate dehydrogenase. Unlike all of the enzymes in the citric acid cycle, succinate dehydrogenase is embedded in the inner mitochondrial membrane and also a component of the electron transport chain, and of which it is also called complex 2. As complex 2 oxidizes succinate, it receives 2 electrons that will ultimately pass on coenzyme Q, which in turn will deliver its electrons to complex 3. Another interesting aspect of complex 2 is that it uses FAD rather than NAD+ to accept electrons. In the 7th step, fumarate is converted to malate by the enzyme fumarase. And finally, in the 8th step, the enzyme malate dehydrogenase oxidizes malate to reform oxaloacetate and reduces a molecule of NAD+ to NADH. In the process, this regenerated oxaloacetate can then combine with another